All right, standing waves. A standing wave is a wave which is reflected back and forth until it creates a pretty pattern, basically. A standing wave, like we demonstrated the other day with the string and the vibration, like a guitar string would undergo standing wave pattern. When it's plucked or when a frequency is generated in it, it generates a nice, pretty pattern of nodes and antinodes. Instruments do this as well. Instrument shapes are designed in order to create nice frequency patterns, or wave patterns rather, in them. These reflection patterns can happen either in open tubes like this, or tubes which are closed on one end and open on the other, or it can occur on strings which are tied down at both ends. And there's different patterns for different one of those, and you need to memorize these patterns. When the waves bounce off of each end, they come back and they interfere with each other. And when they interfere in a very regular way, they create a nice standing wave pattern. What that does for sound is it amplifies the sound. So in a tube like this, which is closed at one end and open at the other, there are certain distances at certain frequencies which will amplify the sound. And we're going to listen to a couple of those later on. With tuning forks, you can't really hear the tuning fork unless the tuning fork is very, very close to you. Now you can use this to amplify the sound, but only at certain distances. So right now, this distance is not doing anything as far as amplifying the sound. However, modify that distance. You might hear the sound amplified some. Yes? Now, if it's not at that distance, you don't hear the same amplification. The reason you hear the amplification is because at that distance, at that frequency, a standing wave pattern is being generated. Instead of the waves bouncing back and forth and being all jumbled up in obscure fashion, the waves are bouncing back and forth and creating those nice patterns that we saw with the wave generator the other day. For a fixed end string, so when a string is tied down at both ends, because it's tied down at both ends, it has a node at both ends. And these fixed positions here are called nodes. The larger positions here is represented by the A. The maximum amplitude is called the antinode. Now, one wave consists of two antinodes. So this is the first harmonic. It's the first standing wave pattern which will occur when the two ends are fixed down. How much of a wavelength is represented by this first harmonic? Is that a full wave? It's a half of a wave. So in the first harmonic for a fixed end string, it is only represented by half of a wavelength. The second harmonic, or the second pattern which can emerge, it must be fixed at both ends. So the only thing we can do is add a single antinode, or a single node right in the middle. When we add a single node in the middle, it becomes the second harmonic. And how much of a wave or waves do we have in the second harmonic? We have a single wave. So the second harmonic is represented with one wavelength, or 2 over 2 waves. 1 over 2, 2 over 2. What do you think the third harmonic is going to be? 3/2 wavelength. And if we look at the pattern, there's one wave, and there's a half of a wave. The fourth harmonic, how many waves would it represent? 4 over 2, or 2 full wavelengths. And these are the only harmonic patterns that can occur for a fixed end. 2 nodes at the end. We can create a general pattern with only half a wavelength or no nodes. 1 node, 2 nodes, 3 nodes, 4 nodes, and so on. It's much, much easier to memorize the pattern than to memorize what each one of them looks like. But you're going to be asked, what's the third harmonic on an open fixed string? Or not an open fixed string, but an open fixed pipe. Or a tied down string at both ends. And you'll need to draw that, calculate the wavelength, velocity, frequencies, and things like that. And this is just kind of a review of what we first went over. Looked at it from a different perspective. The first harmonic, also known as the fundamental frequency or the fundamental harmonic, if it's tied down between positions, a length of L rather, there's only 1/2 of a wavelength. So 1/2 of a wavelength in the distance L means that one wavelength is actually 2L. See the mathematics there? So we start by saying, how much of a wavelength is there? There's 1/2 of a wavelength. And that 1/2 of a wavelength here represents the full distance L. So multiply by 2, and we end up with a wavelength that's twice the distance between the posts. For the second harmonic, try to do the math first. How many waves are in the second harmonic of a fixed string? Remember? One full wave is the second harmonic. So the second harmonic here, one wave, or 2/2, equals L. So the wavelength is L. Second harmonic is also known as the first overtone. There's a bass tone, and then there's an overtone, and there's a second, third, fourth, fifth overtone. Hypothetically, there's an infinite number of overtones. What about the third one? How many waves are in the third one? 2/3. 3/2. Oh, you get into the next, yes. I don't know which one you're talking about, but 2/3, 3/2 of a wave equals L. So a wavelength is 2/3 the distance L. Is that where you're going with that? Step ahead. Open waves. Now in open ends, you have an antinode at both ends. So this pipe would represent an open instrument. You have an antinode at both ends. Instead of being fixed down and held, there's nothing there. So it represents an antinode. When you have an antinode at both ends, the first harmonic has a single node. There's no harmonic that's just that. It's not a harmonic pattern. Harmonic patterns are wave patterns. So the first harmonic that we can have has one single node in the middle. How much of a wave is that? It's from a crest to a trough, so that's only 1/2 of a wave. So the wavelength is twice the distance L. What would the next one be? You still have to have antinodes at both ends. We already have a single node on this one, so we must have 2 nodes. So when we draw the wave pattern, how many waves are there? 1. There's only a single wave there. It's a crest to a trough, back up to a crest. A single wave. So the wavelength equals L in this case. Next one. How many nodes are we going to have in the next one? We'll have 3 nodes in the next one. Antinodes at both ends. We'll have 3 nodes. And once you start to draw them a little bit, you'll start to figure out the patterns here. Antinode, ends at antinode. How many waves do we have here? 1.5 waves, or 3/2 waves, equals L. So the wavelength is 2/3L. They're the exact same as the fixed end. So open and fixed are the exact same relationships here. Let me go through that. Now a mixed standing wave is the only one that's different. So far we've talked about fixed and open. Now we're going to fix one end and open the other. When we fix an end, what do we have? A node or an antinode? We have a node at a fixed end, and what do we have in an open end? An antinode. So the first harmonic here like that. How much of a wave is that? It's a quarter of a wave. So 1/4 of a wave equals the distance L. So what's the wavelength? 4L. Node, antinode. How many nodes will we have in the middle of the second? Of a single. Got to have a node here. That's how I know how to come back up. How many waves is this? .75. It's 3/4 of a wave. So that's half, and then a quarter to get to the next one, just like our first. So what is the wavelength equal here? 4/3 L. Next overtone, node at the fixed end, antinode, 0, 1, 2 nodes here. How many waves? One and a quarter, or 5/4. So the wavelength is 4/5 L. Instead of memorizing these values here, which you're going to need to know in the end, what you should do is learn how to draw them. And then every time it's indicated that there's a standing wave pattern, take 2 seconds and draw these diagrams. It'll help you get a better visual of what the wave looks like, how many wavelengths, what the length of it is, and so on. Yes, Sam? Yeah, there is an equation. We can come up with it. It's some n equation, n plus 1 over 4 is L or something like that. I don't know how to write it mathematically, though. But yeah, 1, 3, 5. And the other ones are very similar to that. We did the math here. This was 1, 2, 3. The other one was 1, 2, 3 as well. I mean, yeah, there's patterns and there's mathematical equations for that. I don't know if they're not on your formula sheet, so you don't get them. The best way to do it, because you have to draw them anyway. Half the questions about harmonics say draw the standing wave pattern. So you have to know that there's nodes, and you have to know that there's antinodes, and you need to know when they occur and how they occur.